These are the notes on stars. These are the things I'm going to emphasize from Unit 8, Lesson 1 in the textbook. Notice I'm not covering everything, but there are a bunch of little things I think the textbook does a great job showing you. And then these are just things I want to emphasize in addition. We started off talking about the universe and the galaxies that are in it. Remember, those galaxies formed out of the clumpiness of the web structure in the early universe. If those clumps had not existed, then gravity would not have been able to outpace the expansion of the universe, and we wouldn't really have places like this. Now, if we zoom in on a galaxy, by the way, this happens to be that very galaxy that is moving toward us, just like this, the one that's going to collide with our galaxy in about 4 billion years. That is the Andromeda Galaxy pictured there. So would that be blue shifted or red shifted? If it's coming toward us, blue shifted. And then within the galaxy, of course, there's many, many stars. And we already mentioned, well, there's other things in the galaxy other than stars, like a lot of nebula and dark matter. But we're going to emphasize the stars. Here we see a close-up image of the surface of a star. The only star that we can really see close up, because it's the one that we're orbiting around, our sun. If you look at the surface of the sun on this extreme close-up scale, what does it look like to you? Does it look like a liquid? Does it look like a gas? Maybe even a solid? It actually turns out to be none of those things. So we're going to be learning about stars and what we call stellar evolution, which actually has nothing to do with biological evolution. It's about the star's life, the life cycle of a star. We have to know a little bit about this to understand our place in the universe. So if it's not solid or liquid or gas, you should be able to tell me what it is. What is it? It must be plasma. Plasma, of course, is the fourth state of matter. It is completely ionized gas. So what that means is it's not gas anymore. It's something else. Kind of like you could say gas is evaporated liquid. It's not liquid anymore, right? So what does completely ionized mean? If this is an atom, this would be magnesium. Well, look what's happening. Where'd the electrons go? Well, if the electrons get removed from an atom, it is no longer an atom. It is what we call an ion. And if you get completely ionized, that means you don't just lose one or two or pick up one or two electrons. You actually lose all of them, and they're just scattered around. Now, this is what happens when you have extreme conditions. When you have extreme pressure and extreme temperature, it is impossible for the atomic structure to be stable, so the electrons get knocked away. And then, of course, well, that ion wants to pick up electrons again, so it might pick them up again, just to have them knocked away again repeatedly every few microseconds. So it's just this big mess where you get all these ions floating around, all these cations, the nuclei of atoms, without their electrons going around, and the electrons are going in other directions, all flying around at extreme velocities under high pressure. That is what we mean when we say plasma. We do find plasma on Earth. Every time you see a lightning bolt, that is plasma. Now, we have two different words for lightning and thunder. It's funny that we don't have one word to unify them. I thought of Thor's fury, but nobody's going for that one. Plasma is the most common state of matter in the universe. Well, we don't know about dark matter, but of the ones we know about, because all the matter in stars is in the form of plasma. Even some of the matter in space is in the form of plasma outside of stars. So it's actually a very, very common state of matter. So it's very important to know about. So again, plasma is the fourth state of matter. Solid, liquid, gas, we deal with those on an everyday basis. And then the fourth state of matter is plasma. Of course, plasma is ionized, meaning that it can conduct electricity. Well, some solids can conduct electricity, and liquids that have some kind of solute in them. Solutions can conduct electricity, but gases never do, interestingly. Gas will not conduct electricity, but plasma will. So if you ever see something that looks like gas that conducts electricity, well, that must be plasma. Also, our sun conducts electricity. There's a lot of lightning in our sun. You might not have been aware of that. Also, Jupiter has a lot of lightning. Earth is not the only place with lightning. Actually, here in Southern California, it might not seem like Earth is a place with a lot of lightning because we only get about 5 thunderstorms a year. It's very infrequent, one of the places on Earth that gets the fewest. People will bend over backwards to not talk about plasma. A good example, in our textbook, if you turn to page 480, there's a little thing explainer called Our Star, and they try to describe the sun using the 1,000 most common words in English. Well, they have to bend over backwards not to use the word plasma, of course, because that's not one of the most common words. And it's kind of cute, but I don't know how effective it is. Let me know if you think it's useful. But we can't fully understand what goes on inside a star unless we understand plasma. Also, one thing I want to mention is that most stars are not just a star on its own, a lone star like our sun. Most stars are actually binary stars, meaning that there's 2 of them orbiting each other. It's kind of hard to say sometimes which one is going around which one. They're kind of both orbiting that red circle there, which is what we call their center of gravity. They sometimes are orbiting a position that has nothing there, okay? And this happens quite a lot in orbits, but a lot of people like to think, okay, the Earth is going around the sun, but actually we're going around our center of gravity with the sun, which is actually located inside the mass of the sun, just not at the very center. And it's even further from the center for planets like Jupiter, because Jupiter is a more massive object and it's further away. So just keep in mind, we like to simplify things and say, the moon is going around the Earth. But again, the moon is orbiting around the center of gravity between the Earth and the moon, which is inside the Earth, but it's actually 3/4 of the way out from the center. It's closer to the surface of the Earth than it is to the center of the Earth. So these are things we don't usually have time to get into, and I'm not going to have much time to get into binary stars, which is actually the most common way for supernovas to occur, is with a binary star. So just keep in mind that actually, despite a lot of what you read, most stars are not on their own. They're in pairs or in multiples where there's 3 or 4. We can just call those all binary for simplicity's sake. 4 stars, 5 stars, 6 stars, okay? For example, the star Pollux in the Gemini constellation is actually 6 stars. So there you go. It's actually not that rare to have multiple star systems. It's actually more common than lone stars. Our sun, however, is a lone star, and it is the one that we have learned the most about because it's so close to us. It's not a light year away. It's not even a light month away or a light week away. I guess we don't really use light weeks. Light day. It's not even a light hour away. It is a little bit over 8 light minutes away. So when you see the sun, you're not seeing it as it was years ago. You're seeing it as it was just a few minutes ago. Look at this picture. Doesn't this picture resemble a colorful cloud? And that's what it is. A cloud, in a sense, floating in space, a space cloud. Well, we like to be fancy, so we don't call it a space cloud. We like to use the Latin word for cloud, which is nebula. So we call this a nebula in space. A nebula in space is usually made of the most common elements in space, which are hydrogen and helium, but then they always have a bit of some of the other elements. Depending on the particular nebula, they sometimes have more of the what we call heavier elements, the elements that we might be more familiar with here on Earth. Okay, and here you can see different kinds of nebula. Some of them are glowing, like that red one, okay, is an emission nebula, and you can see some that are dark, that are absorbing light. They call those absorption nebula, like that little one in the center that looks like a chess piece. That's called the Horsehead Nebula. It looks just like a knight in the game of chess. So a nebula is important to us because that is how the sun formed, and that's how the planets formed, including the Earth. So to know a little bit about our place in the universe, we have to understand what a nebula is like, or what it can be like. That nebula, unfortunately, is no longer around, the one that formed the sun and the planets, because most of it was incorporated into the sun, a little bit into the planets, and the rest of it was blasted away when the sun ignited, so to speak, when the sun lit. So, nebulae are the birthplaces of stars and planets. Nebulae, by the way, is the correct Latin plural. Most people will probably say nebulas, which is somewhat acceptable, but this is the correct plural. It's just a weird ending, AE. Well, how do we know this? Well, we can sometimes see this. These stars are called the Pleiades. They have recently formed out of a nebula that has not dispersed yet, and you can still see the remains of the nebula they formed out of around them. Okay, they're shining a light on it, and it's reflecting their light back to us. So how does a nebula form a star? Well, remember, we were talking about gravity. Gravity really attracts any two masses. So every little part of that nebula has mass, and every part of that nebula is attracting every other part of that nebula. So what it tends to do is pull the nebula together. If every little bit is pulling on every other bit, eventually it makes the nebula smaller, and then the attraction increases over shorter distances. Eventually the nebula contracts until sometimes you get to a high enough pressure and temperature when you can begin nuclear fusion, and that's when you have a star. Then the star goes through its life cycle, and it has a bunch of possible outcomes depending on its mass, depending on how much mass from the nebula went into the new star. That is the principal thing that determines what happens to the star. So watch this star's life cycle. Here the star forms out of a compressed nebula. That's when fusion begins. That's the beginning of the star's life. And our sun is in the middle of this main sequence portion right now. About 5 billion years from now, this will happen. And notice how the sun blasts off some of its layers into space, forming a new nebula, and that goes into the next generation of stars. That is called a planetary nebula. It only has a little bit to do with planets. It's just that from a distance, the shape is very spherical, kind of like a planet looks spherical. So when they saw them originally, they thought they looked like ghostly planets. And then we already mentioned that that's the leftover remnant of our star in the middle, the brown dwarf, which it eventually cools to. So the effective lifespan of our sun is around 10 billion years. We are very close to the middle of that lifespan right now. We are at 4.55 billion years, and we expect there to be a sun in the sky pretty much the same, looking very, very similar in what we call the main sequence for an additional 4 to 5 billion years before the red giant phase, and then the explosion that throws out a new nebula into space. And then after that, you really have the aftermath of the sun's life. You have a cooling off period, which is not when it's actively fusing, so it's not considered to be part of the star's lifespan. But not every star follows the same pattern. Some stars form out of less nebula. Some of them form out of not as much matter. They are what we call low mass stars. Our sun, by the way, is kind of a typical average mass star. It's kind of in the middle range. If you have a low mass star, here's what happens. Less nebula goes in, you can still get fusion, and you still get a star, but that star doesn't do anything dramatic in its lifespan. It just goes through its entire life with a very, very tiny core, which is an important part of the star where fusion occurs, and it lasts for a very, very long time, much, much longer than the lifespan of our sun, but notice nothing dramatic happened there. Here that animation is again with the parts labeled. Small nebula, fusion ignition, and then you get a white dwarf, or not necessarily a white dwarf, but a low mass star. And it goes through its entire lifespan, potentially up to 100 billion years, which is far longer than the lifespan of our universe so far. So these stars, if they formed early in the universe, would still be around. If, on the other hand, you have a much more massive nebula that forms the star, you get a much more massive star, a heavyweight star. You might imagine it would last a long time with all that fuel, but it doesn't. It can explode very, very quickly, forming what we call a supernova. These massive stars have a very short lifespan because they also have a massive core. Here is the animation labeled. A large nebula forms that heavyweight star, very short lifespan, less than 1 billion years, sometimes much less, and then a very massive explosion. Okay, and this leaves behind a supernova remnant, which can be, among other things, a neutron star or even a black hole. This is how some of those exotic members of the universe form. The strange things we find in our universe form often from a supernova. Also, a supernova is incredibly important to the rest of the universe, even though they don't happen that often, because this is the way that some of those heavy elements are formed and enrich future stars and future planets. So there is a relationship between the mass of a star and its lifespan. This is a relationship that we see all the time in science. Watch, this is the same relationship that we find between temperature and viscosity. Okay, let's say of magma or lava. The temperature and viscosity of magma and lava have this kind of relationship. When the temperature gets colder, the viscosity increases. When the temperature gets hotter, the viscosity decreases. So in other words, lava flows faster when there is a higher temperature. This is what we call an inverse relationship. It is an upside down relationship, like inverted, flipped over. And we find this with many, many quantities in science. So in this case, I'm not talking about temperature and viscosity of magma. I'm talking about the mass of a star and the lifespan of its star. Those have an inverse relationship. So a very, very massive star, that heavyweight star we saw at the end, had a very, very short lifespan. And then the very, very low mass star that we saw had a very, very long lifespan, longer than the length of the universe so far. And then, of course, stars in the middle of the mass range have a lifespan in the middle, like our sun has a medium length lifespan. That is what we call an inverse relationship. So what makes a star a certain size? Notice I've only been talking about the mass of a star, not the size of a star. Those are not to be confused because stars actually have very variable sizes. They can grow and shrink depending on their output and their mass. So anytime you see a star, you've got to realize that it's always in an equilibrium, which is a balance between the energy pushing out, generating pressure, and the gravity, which always wants things to get smaller. Gravity really would love to pull everything together into one point. That's what it wants to do. But a lot of things fight against gravity. In this case, the energy output of the star, which is formed in the core of the star, the center of the star. So imagine, gravity wants things to shrink, and it would do that, unless energy is pushing back out against it. So between those two competing forces, what you wind up with is the size of the star. Now, stars are also very, very tricky to put a circle around and say the star ends here, because stars don't really end at a very specific point. They kind of keep going out into space, and we don't usually recognize that. But our sun actually, in a way, continues far beyond the orbit of the Earth. There's something we call the solar wind, which is actually part of the sun, and it continues out to the edges of the solar system. So when you look at the structure of our sun, which is similar to the structure for any star, the most important part of a star is really its core, because that is where the fusion happens. That's the part of the star we really need to know about to understand what is happening. The only problem is we can never see the core of a star. What we actually see, what we call the surface of a star, is its photosphere. The photosphere is what you would take a photograph of. Okay, when you take a picture of a star at night, you're getting the photosphere. Picture of the sun, you're seeing the photosphere. It's where the light is emitted. So we have to judge stars not by their cores, which can almost always be in the millions of degrees Kelvin or Celsius. We have to judge them by their photospheres, which are much, much cooler, usually only in the thousands of degrees Kelvin or Celsius. So just keep that in mind. The part of the star we're observing when we're talking about these temperatures is not where it's all going on in the core. We're talking about the outside of the star, the surface, the photosphere. Another issue about the star's structure, or the sun's structure, is the size of its core. The size of the core determines how much nuclear fusion can occur. And look at the size of the core of our sun. It's relatively small, okay? But if you have a low mass star, the percentage of the star that is a core is even lower. It would be a tiny little blip at the center. And if you have a massive star, the percentage of the star that is a core where nuclear fusion can occur becomes much, much larger. That is one of the reasons that these massive stars have such short lifespans, because their core is much, much larger, meaning they can burn through their fuel at a much faster rate. I'm just going to briefly mention this about star brightness, stellar brightness. There's what we call the apparent magnitude of a star. So if you look up at the sky and you see a star, that's how bright it appears to you. Okay? This depends on how big the star is, how hot it is, and how far away it is. It depends on a lot of factors. If a star is closer to us, well, of course it's going to appear brighter, just like a flashlight appears brighter when it's right near your face, shining in your face, than it does if it was across the room, shining at your face. And a flashlight is going to appear brighter when it's in your face than a car's headlights if they're a mile away, but you know that those are truly brighter in an absolute sense. So what we have to do for stars is calculate how bright they really are. That is the absolute magnitude. That's if every star was the same distance away, how bright would they appear? They chose the distance, what we call 10 parsecs, or 32.6 light years away, and they calculate how bright a star would be at that distance. So some stars are right in our face, like the sun. So it has a very, very bright appearance. But its absolute magnitude isn't really that extreme. Now, I've got to mention, magnitudes are kind of an upside down scale. Because of the way they began to rank them back in ancient times, they would say a star of the first magnitude. That was a very bright star. And a star of the second magnitude was not as bright. And a star of a third magnitude, not even less bright. And in fact, we can only usually see down to about the fifth magnitude. Those are dim stars. So because of the way they did that back in the old days, the scale wound up sort of upside down. 1 is brighter than 2. 2 is brighter than 3, and so on. And now we know that there are stars that are way brighter than the ones we just happen to see in the sky, going into the negative range. So because of the way they originally set up magnitudes, the magnitudes that have lower numbers are brighter, and 0 is brighter than 1, and -1 is brighter than 0, and you can get increasingly more negative for the brightest stars in the galaxy. -5, -10, those are extremely bright stars. So keep in mind, magnitude is an upside down scale. Another thing to mention is that it's logarithmic. So every time you go down a magnitude, like from 1 to 0, you're actually getting 10 times brighter. So it's a very dramatic change, not just a little change here. Anyway, so you can see on the table, and there's one similar to this in the book, that just because a star appears bright, let's say has a low number for its apparent magnitude, like our sun is -26.7, doesn't mean that it's actually a truly bright star. Look at its absolute magnitude. Our sun is just a 5. Okay, remember, 5 is much dimmer than -27. And other stars might not appear as bright as they truly are. Like look down at the bottom, Deneb. Well, Deneb is a very, very bright star. Its absolute magnitude is almost -7. That is incredibly bright. However, it's very, very far away. It's 1,600 light years away. So it just doesn't look that bright to us. It looks about 1.3 magnitude. Okay, well, that's bright in our sky, but not nearly as bright as it truly is. So the way that we classify stars is using something that we call the Hertzsprung-Russell diagram. That is a mouthful to say, and it's really hard to spell. It's probably even harder than Fahrenheit or Van de Graaff. And so people don't usually say Hertzsprung-Russell, they say HR diagram. So you can call this an HR diagram, and it plots the absolute magnitude of a star on the left. Notice those go from +20 on the bottom, that's very, very dim, to -10 on the top, which is very, very bright. So again, it's an upside down scale. The negative numbers are brighter. The positive numbers are increasingly dimmer, okay? And the temperature on the bottom. The other thing strange about the HR diagram is the way they have temperature. They don't start on the left with the coolest temperatures. They start on the left with the hottest temperatures. So that is also kind of reversed to the way we're used to. Most things we graph, we start with the low numbers near the corner of the axes, and then we increase as we go away from it. But not in this case. In this case, the coolest stars would be the ones way off to the right, the ones that are red. Turns out, despite what a lot of people seem to think, blue stars are way hotter and red stars are way cooler. We have this strange association of red with heat, but it doesn't really work out with stars. So the red stars have the coolest surfaces. Usually they're the coolest stars overall as well. So when we want to look at stars' life cycles, well, we want to look at different masses of stars. A, B, and C here represent a low mass star, a medium mass star, and a massive star at the bottom. C is a massive star. So notice that the outcome for these stars is very different. Their life cycle is very different. B is the one that is like our sun, very, very much like our sun. That's a typical star's life cycle. A is an itty bitty low mass star that has a very, very different lifespan, much, much longer, because remember, it's inversely related. And C is a massive star, which has a very short lifespan, because remember, it's inversely related. The massive stars are the most interesting because their brief lives give rise to dramatic explosions and exotic objects in our universe, and it enriches our universe with the heavier elements. The life cycle of our sun is interesting as well because, well, we're orbiting around it. That's the most important star to us, and it kind of typifies the life cycle of many stars in our universe. So here is an HR diagram showing many, many things. It's got absolute magnitude on the left side. I'm trying to show that the -10 is the brightest. Hopefully you realize the ones at the top are the brightest. The ones at the bottom are the faintest. I'm only going down to +15 there. That's very, very dim. Okay. Also, the temperature is along the bottom, hottest on the left, coolest on the right. And notice how that very, very closely corresponds to the colors of the stars. The blue stars are all the hottest stars, and the red stars are the dimmest stars for the most part. The only exception would be the giants and supergiants, which seem to sort of buck this trend a little bit. On the top, we have the spectral class, O, B, A, F, G, K, M. Those correspond to the color of the star and also to the temperature of the star. All right. So you'll notice that very many stars fall on a diagonal, going from the top left to the bottom right. This makes sense because don't you think a hotter star should be brighter? And so the ones on the top left are the hottest and the brightest stars. And don't you think that the coolest stars should be the faintest? Well, that makes sense. And those are the ones down on the bottom right. And then everything in between sort of corresponds to our expectations. Those are your typical stars. Those are what we call the main sequence. Now notice how there are no green stars. Interestingly, the way it works out because of the black body radiation temperature curves, which the textbook does a good job showing, look at those, there's nowhere that the average of the colors appears green to our eye. So there just aren't any green stars. That's why I'm using green for some of my labeling, some of my, where it says main sequence, I'm using the color green because it wouldn't get confused with any of the stars there, okay? So the main sequence is where 90% of stars are found. It is where our sun is found as well. It's where most stars are found for most of their life cycle. And only briefly do they exit this main sequence. The only exception to that would be the white dwarfs that can remain there for quite some time. So when a star becomes a giant or supergiant, it's just not going to be there for very long. We don't have enough time to go into great detail about that, but you just can't remain a giant or supergiant for a long period of time. It just doesn't happen. So we're going to plot on this HR diagram the life cycle of our sun. It doesn't really begin on the table because a nebula doesn't have fusion, and so therefore it doesn't fall directly on the HR diagram. So look where I'm putting it. A little bit off the diagram to the right. A little bit just off the diagram. That would be a nebula floating in space. Well, that's the way that a star begins, from a nebula compressing until it gets nuclear fusion. So watch what happens when that nebula begins to have fusion. It joins the main sequence for a time, and then we'll follow the path of our sun's life cycle. Here we go. Joins the main sequence, most of its life, then it exits the main sequence, swells up, minor explosion, becomes a white dwarf, and then cools off, ending its life as a brown dwarf. This is what we expect to happen in our sun's life cycle. Here's the pathway it followed. So our sun right now is located right about there where it's flashing. That's what we call a G-class star. Our sun, if you didn't know this, is a G-class star, or a yellow star. And that just has to do with its temperature and the wavelengths that a black body emits at those temperatures. And again, look at the diagram in the book for the black body emission curve. So looking where our sun is now, its main sequence, in the future it will become a red giant briefly, and then it's kind of a dead star just cooling off to a brown dwarf or a stellar remnant. It's interesting to note that stars undergo nuclear fusion. To be a star, you have to have nuclear fusion in the core of the star. That nuclear fusion goes from hydrogen to helium, then it makes carbon and oxygen. There's a really good sequencing of it in your chapter you're going to see. But most stars will not produce any elements beyond iron, and iron is only number 26 on the periodic table. So for the very, very massive elements that we find here on Earth, and even in our sun, they need to form under very particular circumstances. And that is when a massive star goes supernova. So the reason that we're so obsessed with supernovae is that they produce many of the elements that we need. Things like silver, gold, platinum, uranium, the heavy elements, lead, the heavy elements that we find here on Earth were not formed in your everyday run-of-the-mill star. They are only formed in the very, very massive stars. So the death of a massive star is called a supernova. We're not going to go into great detail about this. Technically, to have a supernova, many times you actually need to have a binary star, which is lucky because most stars actually are binary. But there's several different ways a star can go supernova, and one of the ways is just being ridiculously massive. Another very important topic that is covered in this section is about spectral lines. Spectral lines are the way that we know what stars are made of. It's also the way that we know what distant galaxies are made of. This is very, very, very important to us. Spectral lines are the wavelengths of light released by hot gases and plasma. And it's the way that we can tell the redshifts of galaxies, because in order to tell how much light is redshifted, you have to know exactly what wavelength it started as. So the problem with spectral lines is it's a very hands-on thing. The textbook does a pretty decent job of showing you pictures and diagrams. So definitely you're going to be looking that over. But I would love to do the lab with you. You may have done this lab if you were in my chemistry class last year. If you were in my chemistry class, you may have already done a spectral lines lab. But I usually like to do it with physics as well. And if we do go back to school, if we are there, I might just throw this lab in because it's just a great lab to experience. Okay, understanding how the spectral lines appear and how we measure them. So spectral lines can be observed with a spectroscope, which has an interesting etymology, the origin of the word. The word spectral has to do with seeing ghosts, because if you think about it, a spectrum or like a rainbow, if you see a rainbow, you can see what's behind it. It's kind of transparent, kind of ghostly, okay? And a scope is something you use to look at something, so a spectroscope actually means a ghost viewer. It's kind of a funny etymology. This is the instrument we will use in our lab if we get the chance to do it. I tried to find a way to make a video for this lab. I tried many different techniques of photographing it. It turns out I was able to get still photographs that worked out pretty well, and you could see the lines as you can see here. And then I was able to put them against calibration, but I was never able to get a satisfying video where you could sort of see how the measurements are taken and what they really look like. So I did take some photos. I figured out kind of a way to do it with still photos. It didn't work as well with moving pictures with video. And on the left, you can see the bulb of hydrogen, the most abundant element in the universe. It turns out it looks a little different to your actual eye than this photograph makes it look. The color looks a little different. But on the right, you can see the markings that we find inside the spectroscope, the 4, 5, 6, 7 for the 400, 500, 600, 700 nanometers. And I managed to match up the spectral lines that I photographed from hydrogen below that. But it just doesn't quite get the point across. You have to kind of see them yourself. Helium, notice, is very different, so at least you can see that it's not the same spectral lines for hydrogen and helium. That's how we're able to tell where there's hydrogen and where there's helium in the universe. Interestingly, helium was discovered by looking at these spectral lines coming from our sun. That's why it was named after the sun. Helios is the Greek god of the sun, so that's where it got its name. Okay, so again, if we go back, while I still have you guys for students, I would love to do a spectral lines lab so you can do a hands-on experience looking at these lines that tell us so much about the world. So that's the end of the notes on stars. Now, there's many things I'm expecting you to get from the textbook. I did not throw everything in there, but clearly I'm emphasizing certain things. The things that I emphasized in these notes are the things I want you to know more, okay? But then there's other things from the textbook that I would expect you to also be aware of. So as long as you do the assignment, you will have covered those.